In 1903, on a distant set of sand dunes in the far reaches of the North Carolina Outer Banks called the Kill Devil Hills, two unknown bicycle makers from Ohio ushered in the era of aviation history by successfully completing the first piloted, powered flight of fixed-wing aircraft. Now, this first flight only went 120 feet, and it only lasted 12 seconds. In addition to the Wright brothers, there were only 5 other people there to witness the event. 4 men from the local weather station that were there to help with the machinery, and a local boy named Johnny Moore, who just happened to be passing by and thought he'd stop by and see what all this hubbub was about. Of the 7 present that day, 17-year-old Johnny Moore was the one who could have lived long enough to see the other bookend of this era of pioneer flight, the Apollo 11 moon landing in 1966, 63 years later. As a youngster myself, I was, of course, fascinated with airplanes and with flight. I had the pictures, I built the models, I flew the gliders, I had one incendiary misadventure with a model rocket engine. So you can imagine my excitement when an East Coast relative offered to take me to the Smithsonian Air and Space Museum to see the Wright Flyer, the original airplane, the one that started everything. I can still remember as a youngster of 7 or 8 walking into the Wright exhibit, seeing the single-speed Wright bicycle there encased in glass, patiently waiting its hipster revival 20 years later, and then turning the corner and laying my eyes on the Wright Flyer, the machine that started it all. My exact words at that moment were, "What the hell is this? It's got no cockpit, the tail's on the wrong end, it's built with sticks and held together with wire, and why is this guy laying in the middle of it? What is this, an airplane for narcoleptics?" Needless to say, young Andy was appalled. It wasn't until much later that I developed a more nuanced and sophisticated appreciation of the importance of prototyping. And it was much later still that I realized that while modeling and prototyping is important for the validation and testing process, it is equally, if not more important, for the learning and creation process, particularly when it comes to the kinds of complex problems that we face as information architects. Now, as unlikely as it may sound, the Wright Flyer is an excellent example of this process in action. So, let me tell you a story. Let me tell you a true story this time. Though the Wright brothers are credited duly with powered flight, before they solved the 1903 problem of power, they first solved the problem of how to control an aircraft in flight. Lift and power were technical problems. These were problems that the Wright brothers knew would eventually be solved. There were lots of people working on this at the time. The problem of pilot control, however, had no precedence. Aerospace research engineers Padfield and Lawrence write that the invention of the powered airplane in 1903 somewhat overshadows the earlier critical flight control developments. Padfield and Lawrence and others, including the curator of the Wright exhibit at the Smithsonian, date the birth of the airplane with the 1902 glider. Now, this problem, while also technical, this problem of control, was at its core a human problem. The Wright brothers needed to solve for how humans behaved in the complex system of machine, environment, and human agent that they were working to construct. The Wright brothers used a process of modeling, simulation, and iteration to learn from each version of the glider and the flyer they built. They also assiduously limited the variables in each version that they tested to ensure that they understood how the system worked together as a whole. Now, we can see this process of limiting variables in their very first ideas about control, whereas their competitors, and there were many, were looking to contemporary models of passive and stable control, like rudders on ships. And remember, cars still had tillers at the time, right? Also a rudder model. The Wright brothers, being bicycle makers, were convinced that the best way to steer, and crucially, to correct unintended direction changes, was by banking the machine, leaning it to one side, much you would a bicycle, not trying to turn it on a flat plane as though it were sitting on the ground like an automobile or floating in water like a ship. To test this, they began by developing a system of wing warping. This is based on their observation of birds in flight and, as the story goes, a flash of inspiration when Orville was playing with an empty bicycle inner tube box. By a series of guide wires connected to the ends of the wings and a control harness fitted to the pilot, by leaning in one direction or the other, the pilot was able to change the shape at the tips of the flyer's wings, effectively creating a lift differential on one side or the other that would bank the craft in the opposite direction. The Wright brothers tested this concept with box kites, and then in 1901 with their first piloted glider. This version of aircraft, in stark contrast to the other machines that their competitors were building, had no rudder. For that matter, it didn't have a tail section at all. The concept of a rudder didn't fit with the model they were trying to test, so they left it out, even though it was an obvious piece to everyone else at the time, and it certainly appears obvious to us now. Now, the 1901 glider both did and didn't work as they had hoped. Wing warping did produce differential lift, which did bank the aircraft. But by creating additional lift on one side of the wing, they also created additional drag on that side of the wing. This resulted in a condition called adverse yaw. What it meant was that when the glider banked to the left, it also spun to the right. When it banked to the right, it spun to the left. Not terribly ideal. But they learned from this. And to correct this, they introduced a fixed vertical stabilizer in the 1902 version of the glider. Now, although this meant that the Wright glider formally began to resemble gliders and flyers that others were experimenting with, the purpose and the function of this new addition was stabilization, not control. And it did work. In fact, it worked a little bit too well. The fixed vertical stabilizer did keep the 1902 glider from adverse yaw, so from spinning in the opposite direction of the turn. But it also created a feedback loop in the direction of the bank, making it difficult to right the glider once they had initiated a turn. The effect was that the lower wing ended up dipping lower and lower until it caught the ground, and then it spun the glider around in a circle. They called this well digging. Now, the brothers eventually introduced a pilot-controlled rudder that could be used to counteract adverse yaw and to pull the glider out of a banking turn. This version was modeled in 1902, and then this, of course, was the series of flight controls that they built into the 1903 glider, which they then eventually added power to, and thus we have an airplane. This problem of flight control that the Wright brothers faced in the course of these 3 years is one that in today's language we refer to in systems design as dynamically complex. Dynamically complex situations are ones that have seemingly obvious interventions that produce non-obvious consequences. And the rudder in the Wright Flyer is a perfect example of a non-obvious solution. In the early 1900s, everybody knew what a rudder does. They knew exactly what it did, but it also turns out that this knowledge was catastrophically wrong when it came to aviation. By ignoring the obvious, and in the first versions, leaving it out entirely, the Wright brothers were able to learn about the dynamics of the system they were working in. A second feature of dynamic complexity is that the connections between cause and effect are subtle, and they're hard to spot. Now, in the case of the Wright Flyer, adverse yaw and well digging are pretty easy to spot, right? The results of those, the consequences of those connections aren't difficult. But differential drag and reinforcing banking loops, though seemingly obvious to us now, had no precedent at the time. They had to be teased out. Finally, in dynamic complexity, the effects of interventions over time are not immediately apparent. In the case of the Wright Flyer, the intervention that changed over time was the skill of the pilot. As the Wright brothers learned over the course of these 3 years, a skilled pilot was essential to a working aircraft. Now, this of course seems obvious to us today, I hope, but this was not the dominant thinking of the day. Most of the Wright brothers' competitors sought passive stability over active control, again, like a ship or a car. At best, these machines failed to fly. At worst, they produced spectacular crashes. In retrospect, we can see in this story that the Wright brothers used a process which, though they may not have articulated it themselves at the time, serves as an archetype for solving dynamically complex problems. They modeled in order to explore ideas. They ran simulations on their models in order to learn about the parts of the system they couldn't see, couldn't articulate, and for which they had no precedent. And then they iterated on their model to incorporate what they had learned and then started the whole process over again. This process of modeling to learn is what I would like to discuss with you today in the context of information architecture. How to use modeling and simulation to more effectively solve the dynamically complex problems we increasingly face as practicing designers of information spaces. So, over the next 30 or so minutes, I'll discuss where we encounter dynamic complexity in IA, a modeling approach to facilitate discovery, alignment, and validation of IA solutions, an example of a modeling to learn prototyping process drawn from my own recent client work, and finally I'll point you to an open source toolkit you can use to get started integrating this process into your own work. So, let's start by building some detail around this concept of dynamic complexity. In the classic systems thinking book, The Fifth Discipline, Peter Senge describes dynamic complexity as one of the core challenges we face in designing with, in, and around complex systems. Now, we've already seen this definition come up with the Wright brothers. Senge contrasts this with detail complexity. Detail complexity arises in situations where you have lots of variables, where you have incremental increases in power, speed, efficiency, or scope, and where you have predictable solutions to known outcomes. For the Wright brothers, this detail complexity was the wing and engine complexity. It had to be solved. It was a problem. They didn't know exactly how it was going to be solved, but they knew the technology was there, or it was a linear movement to getting towards that technology. For us, we encounter detail complexity in doing our taxes, in entering our very complicated passwords when our social media accounts get hacked. Dynamic complexity, however, is a little bit harder to spot. Now, we often see dynamic complexity evoked in the literature when we're talking about big social problems. So things like chronic homelessness, the school-to-prison pipeline, global warming is the example that gets used all the time. But dynamic complexity doesn't only exist in large-scale systems. Now, we've already seen where the question of pilot control is a dynamically complex problem. The pilot's abilities, balance, and reaction time are all part of this. Senge also provides an example that hits a little bit closer to home. He asks, who's part of a family? Okay, anybody with their hands not up? Senge, let's talk later, because I'm just curious. Senge then asks, have you ever seen people in families produce consequences that aren't what anybody intends?
Daily.
That's dynamic complexity at a local scale. Now let me adjust this a little bit for our context and ask, who in the room works with clients, on product teams, or with partner agencies? Have you ever seen people in teams produce consequences that aren't what anybody intends? This is also dynamic complexity. As information architects, we're in a unique position to affect these dynamically complex problems because a core element of our work is in building bridges between the different models of thinking. For example, between the models our users understand from their own experience and the models that we define the information systems that we're asking them to use. Now, when I explain this to clients, I describe information architecture as a shim, or a fitting. It connects two fundamentally different systems. And we saw a little bit of this in Bob's talk just a minute ago. One of these systems is carbon-based analog to human system. It's heuristic. It relies on rules of thumb and best practices. It's associative in that it excels at pattern matching and categorization. And it's approximate. It's successful by getting close enough most of the time. It satisfies us. The other system is a silicon-based digital information system. This is exhaustive, it's complete, and it always finishes what it's told to do, even if what it's told to do is to go until it finds an error and then report it back. It's never just going to stop and go watch TV. It's enumerative in that it can account for and recall precise qualities and quantities every time, over and over again. And it's exact. The value is either true or false, on or off. There are no maybes or kind ofs or different versions of what is. IA is the shim that matches what is modeled in carbon to what's modeled in silicon. It's a set of symbolic and conceptual controls that connects one incompatible endpoint to the other. Because these two systems are fundamentally different, there's always a translation here. People don't have the capacity to think like machines, at least not beyond the most rudimentary scale, which is what we use machines for to begin with. Likewise, machines don't have the capacity to think like people, not in a heuristic, associative, approximative way. And you know this if you've ever interacted with your phone's smart assistant. I can't even say that word. So, IA is a set of symbolic and conceptual controls that creates an operable interface between these two systems. It's how we enable each and encourage each to do what it's best at. And it's how we allow each to benefit instead of fight from the strengths of the others. Now, we saw with the Wright brothers how flight controls, the harness and levers, discovered and refined through simulation, provide the interface between the balance, judgment, experience, and skill of the pilot and the lift, thrust, and control surfaces of the machine. Likewise, the information architecture interfaces that we build with symbols and concepts provide the interface between the attention, potential for action, and patronage of our users, and the information access and reach of the data to which we're connecting them. Also, like the Wright Flyer, there are elements of both detail complexity and dynamic complexity throughout these connections. Now, it's tempting to think that all of the detail complexity sits on the machine side and all the dynamic complexity sits on the human side. But the nature of complex systems is that they're hopelessly intertwined. This is a multiplicative relationship, not an additive one. So just like with the Flyer, trying to pull them apart and deal with them entirely separately is usually a failing proposition. Now, some of the places that we see dynamic complexity situations arise in IA project work include user, stakeholder, and content discovery, client organization and workflow, stakeholder priorities and alignment, information model creation and validation, and team alignment and coordination. You notice that these are situations that all universally involve people. But these are also points that are concerned with making IA work for users, but also with stakeholders and teams. An elegant IA solution that's ignored or improperly implemented by the organization that commissions it doesn't do anybody any good. The good news is that by modeling, simulating, and iterating potential solutions, we can untangle these systems to better understand the relationships between their parts and propose solutions that allow each element of the system to contribute according to its strengths. So, let's return to this modeling to learn cycle that we first saw with the Wright brothers and look at how this works for information architecture. For IA, as for avionics, experiential modeling processes like this serve to externalize a problem space, to expose a set of variables, and to make the relationships between those variables clear. Now, for the Wright brothers, we saw that they created models that isolated and exposed the control problem in order to more clearly understand the relationship between banking, yaw, and the rudder. They ran simulations in a controlled environment. Kitty Hawk was chosen both for its steady winds and its soft sands, think landing. And they iterated their model based on what they learned at each step. Now, for us as IAs, we want to model the symbols and concepts that create the connections between user and digital systems, between carbon and silicon. Most often, this means modeling a controlled use of language and vocabularies, such as labels and metadata, an orderly, deliberate categorization scheme, and a coherent set of navigation and findability metaphors, such as menus, page sequences, page layouts, contextual associations. We then want to simulate these models, and yes, we simulate them with users. We do some usability tests, sure. But we also need to simulate them with stakeholders, with developers, with team members. Remember, our goal in this process isn't to vet a concept, it's to learn about the concept, much like in that opening example. We want to learn about the use case, but also about the organization and the technological context in which that use case exists. In dynamically complex structures, we're looking for the subtle, non-obvious, time-delayed relationships. And then finally, of course, we iterate based on what we've learned. And this means updating and experimenting with language, categorization, and layout patterns based on the simulations that we've run. Now, we'll look at each of these steps in detail in a case study that I'll share with you in just a minute. But before we do, I want to talk about this first step, modeling. It turns out that this can be challenging. And it's challenging not because we don't know how to specify or document IA, right? We're good at that. But rather because the tools most readily at our disposal tend not to lend themselves to the next two steps in this process, to simulation or iteration. So let's once again go back to our Wright brothers example and break down what worked well about their model that allowed them to solve the problems that stymied others for so long. We can pick out here a few things in particular that they did that helped them get to the core of the dynamically complex problems they were wrestling with. The first of these was to isolate variables. To test control, they used kites and gliders, so at first, no people, no power at all. And then as we saw, until they knew the purpose it served, they eliminated the rudder entirely. They balanced complexity, so I've already talked about Kitty Hawk's steady wind and soft sand. But they did other things to pull complexity out of the model. For example, in the 1903 Flyer, the first Flyer, they had a tow rope that got it up to airspeed to begin with. It was actually run by gravity from a tower later on. They also, when possible, flew into the wind so that they could generate more lift. Now, these were detail complexity problems that they would have to iron out later on, but they didn't need to deal with those when they were working on the question of control. Finally, they use their experiences to surface feedback loops. Now, this is perhaps the most difficult element of modeling. We have a natural affinity to linear narrative. It's built into the very grammar of our language. In order to understand dynamically complex systems, though, we need to be able to see the relationships between elements as causative feedback loops. These are situations where every element is both cause and effect, input and output, for multiple things. For the Wright brothers, the incremental reintroduction of the rudder allowed them to understand the relationship between banking and yaw. Understanding the feedback cycle was crucial to their final design of a pilot-controlled rudder. So, for us, isolating variables means understanding the impact of the relationship of language, categorization, and structure. Balancing complexity means leaving detailed complexity to the digital systems, they're really good at it, and being able to focus our attention on the relationships that machines don't understand. And surfacing feedback loops means looking for the ways that the human actor is part of the feedback process. So, what does this model look like for us? It's obviously not sticks, wire, and fabric. In the sea of prototyping tools we have at our disposal, however, which approaches best afford us the opportunity to model with language, then to simulate across audiences and iterate easily can be challenging to pick out. Now, this problem has bothered me literally for years. Not too surprisingly, Don Norman offers some insight. Don Norman, in emotional design, identifies 3 levels of processing the information that we find in our environment: visceral, behavioral, and reflective. The visceral level are the rapid judgments about good and bad, safe and dangerous. These are our gestalt perception, our snap judgments, our gut feelings. The behavioral level is the level of well-learned routine operations. So who drives a stick shift? That number gets smaller every year. Do you remember learning to drive a stick shift? It was misery, right? It was terrible. You figured you could never do this. But now you can shift from second to third while eating a bagel, listening to a podcast, and shouting to someone in the back seat, right? No problem. That's the behavioral. The reflective level is sensitive to experience, training, and education. These are our learned skills, such as close reading and detailed analysis of research results, but these are also the elements that reflect our worldview, our values, and our assumptions about the world that make up our core beliefs. Most prototyping tools and techniques target testing and learning between the visceral and the behavioral. What's my impression? Do my well-learned routines work? In order to model the dynamic complexity and the connections between language, categorization, and structure we're talking about today, we need to model at the behavioral and, more importantly, at the reflective levels. To do this, we need tools that allow us to simulate actual content, not filler or a random selection of words, and which allow us to iterate on the quality and structure of that content easily. Now, I like InVision and Sketch as much as the next guy, and I use it all the time. But like Axure, Principal, and Proteo, as well as others, these start from an image of the page, not actual content. Just like our carbon and silicon-based systems, these two approaches are fundamentally different. Trying to get an image-based prototype to behave like a semantic one will always be an uphill battle. So, what tools do we have to build semantic, content, and structure-driven models? The most obvious one has been right in front of us the whole time: HTML and CSS. Now, before I go on and before you flee, let me tell you what I mean by HTML and CSS here. HTML and CSS in production and at scale has gotten bonkers. Like, there are more build systems and frameworks and everything else than I don't know. That's not what I'm talking about. Basic markup and styling is inherently semantic, and it provides the simplest connection between content and the structure that allows users to find it, and the digital structures in which that content is accessed and stored. Now, am I saying designers should learn to code? At a basic level, yes. As type designer Eric Spiekerman puts it, code is today what nuts and bolts were 100 years ago. To fail to learn the rudiments of markup and styling means that we remain ignorant of the medium on which our work depends. So what does this look like in practice? How do we model IA and code in a way that allows us to easily isolate variables, balance complexity, and surface feedback loops? Over the last couple of years, I've put together a loose framework of open source tools that hopefully makes it easier to explore the dynamic complexity of representing information structures in digital spaces. but without getting bogged down in the detail complexity of databases or production code. Now, what I'm going to show you is only one of several ways that you might accomplish the goals that we've discussed so far. Other ways include if you have in-house development environments, or if you have local builds that let you get started in a lightweight way. And I've used those on client projects as well, and that's another great way to begin. If you have to start from scratch, though, here's one way to get started. I call this framework a content-first prototyping framework. It uses a JavaScript task runner called Gulp to string together 4 tools that automate the repetition of generating individual pages from structured content without databases and without server-side operations. Our first step is to create structured content in Excel, right, which is usually where it ends up anyway. Our Gulp plugin, right? Our Gulp plugin takes this structured content and it converts it into an open, readable data format. Gulp then passes that content into the static site generator tool, Jekyll, which is where we can define structure with page templates, reusable content blocks, and global navigation. We can then use the front-end framework Foundation, or you could use Bootstrap if you're into that, to provide basic wireframe styles, and then finally Gulp pipes the whole works into Browser Sync, which serves it up to any browser connected to your local network. Anytime you save a file anywhere along this path, Gulp updates the whole stack and serves up a fresh copy. So our first step, don't start with images. Start with structured content. If you have a content audit, an inventory, or a manifest, you likely have the beginning of structured content. Now, this could be a client roster, it could be a course list, a product catalog, a list of articles. And the example I'll show you today, this is a set of structured content about college programs. And it doesn't have to be exhaustive. If you have 5,000 things, you probably don't need every last one of those, but it should be representative, enough to communicate the breadth and range of the content in question. Now, a plugin, I know this is scary, bear with me. A plugin in our JavaScript task runner, Gulp, converts these discrete chunks of content in our structured content packages into page variables that we can use on individual screens. So in the little curvy brackets there in between the paragraph tags, what you can see are the page variables. So these read page.item title, page.description, page.category. They're basically references to the structured content in our Excel spreadsheet. Now, you can put these in one by one. That would be crazy. Or even better, you can let Jekyll automate page generation across our content sets. So each row in your spreadsheet becomes its own page. Or you can work down a column and output a list of links and labels. This gives us a basic semantic HTML page to which we can add simple wireframe styles. And you're starting from a set of structured content that could be anything from dozens of pages to hundreds. From here, we can use reusable chunks of markup, insert global navigation and wayfinding elements, and then end up with a prototype that we can move through actual content with. Because our model is built and continuously updated from the content out, we're never in a position of having to hunt through pictures of screens to update our content, or to iterate our categories, or to revise our structure. By beginning with the content first, we can more easily simulate and iterate to learn how organizations create and maintain content, how users find and consume that content, and to learn what attributes are necessary to structure and order it in a useful way. We can also iterate on different organizational methods in order to better understand the relationship between each of the pieces in our dynamically complex system. So, what have we done? We've isolated variables that we need to test: language, categorization, and structure. We've balanced complexity by leaving the detail complexity to the machines. It's what they're good at. And we've allowed ourselves to focus on the interdependencies in the systems that we've modeled between user, client, and developer constituents. So these feedback loops, remember, are where everything is both input and output. Term and result. Now, this last point, come out and say, this is the hardest one to grasp. These feedback loops are not things that our language even sets us out to begin to be able to see. This is, however, the crux of where dynamic complexity lives in IA. So let's dig into the details here by looking at an example. I recently completed a project for Shoreline Community College, which is the local campus of the Washington State College System near where I live in Seattle. Now, though advising is available, most students learn about the outcomes, completion requirements, and prerequisites of Shoreline's programs through the program pages section of their website. Now, Shoreline had recently undertaken a visual design refresh of the site, but they found students still had a hard time finding and understanding the options available to them in the program pages section. So, they brought me in to help them untangle the structure and this content and rebuild it in a way that was both findable for students and accurate and maintainable for stakeholders and content creators. Our first step here, working hand in hand with Shoreline's web team, was we started off by interviewing students and building a clear picture of the decision process potential students use to choose a program and where they potentially drop out of that process prior to registration. We identified 3 major steps and 3 potential hurdles that students had to negotiate to start the application process. The first was imagining a potential future. The second was understanding the prerequisites and requirements of a program. And the third was understanding the enrollment process. Now, we chose to focus on the first 2 of these steps, discovering programs and understanding requirements, because these were the places where students were having the most difficulty in the process. Early on, recognizing that this was a good candidate for IA prototyping, I started out by building a model of Shoreline's current state program pages and structure. Using their current program list, a collection of their PDF planning guides, and all of the official and unofficial topics associated with their transfer degree programs. What you see here is an inventory I put together of all their current programs, their categories, and their metadata. Now, even before a single of these structured content elements was represented in clickable UI, modeling the content in this way allowed us to have a conversation with stakeholders that hadn't previously been possible. By seeing a detailed view of the various structures that Shoreline had put in place over the years, such as organizing topics by focus, by area, by concentration, and by pathway, we could start to take apart the range of interests that had shaped their information design to date. And what we found was that there were 3 fundamental forces shaping these categories. They were marketing, accreditation, and instruction. Each of them had a different set of motivations, and those motivations were sometimes at odds with each other. Each of their interests crossed into each other's territory in ways that, while they weren't breaking any rules, were historically very difficult for them to reconcile and to agree on. Now, the tragedy, of course, is that all of these constituents want the same thing, a sustainable college that equips students for success. But each of them are and were beholden to a different set of pressures and viewpoints. With this model, we were able to tease out these interests, and then by putting the content in the context in which it would be used to simulate the effects of potential decisions. And we did this by stepping through the way that stakeholders knew students move through the process. They have years of internalized knowledge about how people get through this process. Our goal was to engage them in a dialogue about user needs that would surface their assumptions and help create alignment in areas where their responsibilities overlap. And to do this, you can see here we built an overlapping set of search and discovery tools with the framework I showed you a minute ago, and stepped through the key points in the user journey that emerged from our initial research. Now, the search and browse patterns that we used here were very basic, and they were at a wireframe fidelity. And this was important for what we were trying to learn. We weren't trying to reinvent navigation. They didn't need something slicker than what they had. We were looking for the right balance of specificity and coverage that worked for everyone. Because all the data came from a single source and updated automatically when we changed, added, or deleted categories, both team members and stakeholders could experience in real time the effects of different configurations. This meant that we could build an understanding of program pages, categories, and structures that the business could agree on, and it also meant that we could immediately start getting input from potential users about which of these structures best help them meet their search, discovery, and information gathering needs. The users in this case, of course, the students. And for this step, we took the same prototype that we had been building all along. We ran a series of moderated and unmoderated wireframe usability sessions that tested the degrees to which our information model matched potential student mental models. Finally, since we've been working with actual content and metadata from the start, when the project moved to development, we already had the data elements that Shoreline's developers needed to implement the system as designed. So, how did this perform according to the criteria we set out with at the start? We isolated variables to discover, align, and validate stakeholder and user needs. We balanced complexity by relegating the content and metadata detail complexity to the prototyping framework. And we surfaced feedback loops to understand the relationships between individuals and the parts of the systems that emerged over the course of our simulations and iterations. Now, this project in particular is still at the end stages of visual design, so I unfortunately can't show you the final. In the meantime, I've posted the repository for the prototype that we built on GitHub. So if you're interested in seeing how it took shape over the course of the project, you can have a look at the commit log there. Now, as I mentioned at the start of this example, this framework is only one way to prototype IA. I wanted to show you a specific series of steps that you could follow, and I also want to stress that this isn't the only way to meet the goals we identified at the start. By way of closing this talk and hopefully of opening the discussion to the innovations that I hope our community continues to bring to this process, I'd like to make one final observation about the Wright brothers. Scholars of the original Wright Flyer have noted that with its anhedral downward sloping wings and its delicate controls, that the 1903 Flyer was so unstable as to be almost unmanageable by anyone but the Wrights, who trained themselves on the previous gliders. After several years of working with the model I just showed you, I'll be the first to recognize that some may find this to be the case with the framework that I just demonstrated. Notwithstanding, what I hope you will take away from this talk is a better understanding of dynamic complexity, of modeling to learn, and of the way that both of these can be applied to IA practice in order to address the complex interdependencies that are part and parcel of our craft. I also hope this inspires you to get your IA off the page and put it in motion early and often in whichever way best matches your skill set. And finally, I hope these ideas taken together set you and your clients up to learn something new, to discover something surprising, and to perhaps create something revolutionary. Thank you.